Good afternoon, everybody. Thank you, Josh, for that very kind introduction, and thank you, Glenn, for founding this program with your colleagues and running it for 30 years. It's really amazing. I'm so happy to see so many of you, returning alumni, counselors, students, present and past. It's really been great to catch up with you and share what we've been doing since and how we view our Promise experience. I was at Promise for 3 years, 1990, 91, and 92, as a counselor, and it really stuck with me all this time, changed my view of mathematics, and changed my life in various ways. So really happy to be here. I learned a lot of things at Promise, and I want to start off our talk today with this. I learned that ideas are exciting. We were encouraged to imagine, to conjecture, to hypothesize things, subject those hypotheses to inspection, and then synthesize what we learned and stitch things together. Ideas were the stuff of our summer. I learned that not all ideas were good ones, but old ideas were worth visiting again. Maybe the idea was bad, but it could be salvaged. Prove or disprove and salvage if possible was our mantra. I learned that it was rewarding to think deeply of simple things. We could eventually get to the hard problems, but starting with a deep, fundamental understanding of the basic building blocks really enabled us to tackle those harder problems with relative ease. And finally, I learned that community research was how it happened. Creative research was not an individual activity, it was a community activity. And by passing ideas back and forth, batting them around, refining them, taking what others had done and building on that, that was the way that we made progress and created research. So these are things I learned at Promise, but I'm happy to say they're also things that I use today. Ideas are exciting. It's a very exciting time to be in my field. Old ideas come back again. You can salvage them. Think deeply of simple things and then move on to the complex. And that research, creative research, is a community activity. So what I'd like to do in the next 55 minutes is to see how these play out in natural language understanding and deep learning, which are the fields that I work in. So the outline of this talk, I'm going to tell you what natural language understanding is and what deep learning is. I'm going to introduce word vector embeddings, which is an interesting core idea. And then I'm going to tell you a little bit about how we got to transformers and BERT before I tell you what those are. And finally, we'll wrap up with a look at some future technologies that are just now coming on the scene. So let's get started. Natural language understanding. So natural language understanding refers to building machines that can analyze, interpret, and generate human language. So there are lots of NLU tasks. For example, identifying whether a sequence of words is actually a meaningful sentence. A second task is to extract the meaning from that sentence in some way, in some format. And then you can start asking about equivalence relationships. Are two sentences meaning the same thing? You can ask, do two sentences, if they're questions, do they seek the same information? If you have a sentence that purports to be an answer to a question, does it in fact correctly answer the question? You can build up from there and ask whether a sequence of sentences makes sense. And then you can get even more ambitious and ask the computer, the machine, to take a meaning and encode it in a natural language sentence, actually generate and write a sentence. And beyond that, you can even ask the machine to write a coherent sequence of sentences on a topic. So actually not just one sentence worth of meaning, but a whole paragraph or text. And these are just some of the many, many ways that we can ask machines to analyze and generate human language. These are all examples of artificial intelligence. I like this presentation from MIT where they broke down a few different concepts. Artificial intelligence is any technique that enables computers to mimic human behavior. We can ask a computer to do any one of these tasks, but we can also ask humans to do these tasks with various degrees of expertise. So we're going to ask computers to do behavior that mimics humans. And here's a fun example of that last one, writing a text. So there's a demonstration you can go to right now called talktotransformer.com. And you give it a prompt, and it will write a text based on that. So I gave it this prompt. Glenn, Margie, and David founded Promise in 1987, with the program opening in 1989. The first year, there were only 20 students, budding mathematicians all. And with that as the seed, the computer generated the rest of the text. I'll just read a little of it. But within just a couple of years, it was filled to the rafters with budding mathematicians from all over the nation. It was an amazing and rewarding experience. There weren't any guarantees that they would make it, and they never had. But I think for good reason. Promise became the brainchild of 4 very dedicated math and physics teachers from around the country. So if I gave this to you and asked you to say, is this a computer that wrote the text, or is this some 9th grade Promise student that came home and had the English assignment to write, "What did you do with your summer?" you might be hard-pressed to figure out which it was. This is an example of a somewhat non-fiction article. Here's another example where the machine can write fiction. The seed that I gave it was, "She handed me a folded-up index card with a mysterious, even nefarious manner. Don't trust me with secrets," it read. That was my seed, right? And the computer from there generated the following text. "I don't believe that all of us who have fallen were taken in by the gods or made into demons." And the dialogue goes on, and it uses quotes and vernacular and he said and she said and the normal conventions of fiction. So these are both entertaining, that a machine can actually generate text in this way, starting from a prompt. The story gets a little scarier when you give it news prompts. Here is the first sentence from a recent Washington Post article. And if you read what the machine generated from there, it is stunningly convincing. So it talks about President Trump making tweets and racist remarks, and then it quotes 2 representatives from the U.S. Congress and their comments in reaction to this. I assure you, none of these people said any of these things, but it's rather hard to discern. You need to know about these 2 representatives who are real people, and they are shown as coming from real places. This is, Jan Sikowski is from Illinois, and Keith Ellison is from Minnesota. But if you look at the views they're expressing, they're not actually what these people said or indeed would believe. But it would be easy to imagine the computer generating millions of these and flooding the social media networks, and every reader now has to decide what's true and what isn't. So these are some scary technology waters we're walking into. But let me walk back to the beginning of the story and ask about some of the more fundamental, easier questions than writing an entire text. So one task I mentioned was linguistic acceptability. Is a sequence of words actually a sentence in the language? It could have meaning, it might need to respect certain grammar conventions, and you can see here some that I've deemed as yes, acceptable, and no, not. That's my human judgment. Another task that you might ask the machine to do is to ask whether 2 questions have the same intent. How can I speak English fluently? How can I learn to speak English fluently? These are probably the same intent. Whereas, does cognition affect perception? Does cognitive strain affect digestion? These are not the same intent. A third question you might ask is, if you have 2 sentences, what is their relationship to each other? Does one contradict the other? Does one entail the other, imply the other? Is there just a neutral relationship between them? So here's another task. And finally, here's the one I mentioned about question answering. If I give you some text, and then I say, here's a question, what's the answer? Can you go through and find from this text, extract the answers? So here's a passage about the science fiction show Doctor Who, and questions about what his spaceship is called or when the show first aired on TV. So natural language understanding is not a new field. Let me give you a brief 60 seconds history of it. It really started out in the 1950s when you had the giants of computational linguistics show up, folks like Claude Shannon with information theory, and Noam Chomsky, one of the pillars of linguistics. So they started putting the field on its foundations. There was work in the 60s at MIT and other places to start building artificial text generators, dialogue, as well as modeling semantics and some statistical approaches to try to identify who wrote certain documents. By the 1970s, you had programming languages that came up explicitly to try to reason about propositions and make logical inferences from one to the other. You also had the beginning of large-scale statistical arguments come up. Hidden Markov models made their appearance in the late 70s. And in the 1980s, you had lots of symbolic manipulation context-free grammars, context-sensitive grammars, as well as further developments of some of these statistical methods. But it wasn't until we got to the 1990s that you got really the statistical revolution, and people started gathering large databases of examples, large corpora of language and labels on them to say this is a sentence or not, this is an answer or not, this is the parts of speech or not. And things really took off then. That's when I started working in it, coincidentally. 2 years after I was finished with Promise in 1994, I started working in speech and natural language fields and have seen what's unfolded in the subsequent 30 years. So that's natural language understanding. Let's talk about machine learning. So machine learning is a subset of artificial intelligence. The folks at MIT defined it as the ability to learn without being explicitly programmed. So rather than some linguist, a graduate student of Noam Chomsky, sitting down and writing into a computer program everything that they know, and then asking the machine to act on that knowledge, instead of that, we want the machine to learn how to do certain tasks without being programmed to do those tasks. And so how could that possibly happen? This is the machine learning framework, and as you can see, it takes a bit of a mathematical turn. There's a set of examples that x1, 2, 3, 4 that live in some space, and they're drawn according to some probability distribution, px. Each example, xi, comes with a label, yi, that says what it is, what its meaning is. These examples and labels are somehow represented numerically. And then we say we're interested in some family of functions that goes from the examples to the labels, takes x to y hat. And the reason I say y hat is that may not be the actual label, right? This is a computed value of x. And what we want is for it to be correct, right? This f is going to be doing all the work for us. And so we want that the outputs of f of x, the outputs of f, are indeed the true labels y, but we don't know that they will be. They are y hat. And so we define a notion of correctness, and in this case, loss or lack of correctness. And so the loss function, L, is something that we decide what's important. If you put in two things that are the same, two identical labels, y and y, you get a loss of 0. So correct means no loss. But anything else, y hat, which is different from y, is got a loss that's anywhere from 0 to unbounded. So you can have things that are different levels of incorrect. And our goal, of course, is to find a member of that family of functions, a little f, that minimizes the expected loss on one example. So you draw an example x according to the probability distribution, you compute its label using the function f, you compute the loss between that output and the true label y, and you take the expected value of this over the entire probability distribution, and we're trying to minimize that, which is to say we want to lose as rarely as possible and be correct as often as possible. And notice that it's not enough for f to memorize the labels of the sample it's been given. At the very beginning, we start with a finite collection of examples. It's not enough for f correctly to label each and every one of those. It needs to do a good job on future draws from the probability distribution. It has to generalize. So that was all rather abstract. Let me give this as a concrete instance. For example, question equivalence. The task might be to assess, are these two questions, q and q prime, the same? So for example, you might be running some internet forum, and people ask questions all the time, and you would like to cluster together the questions that are the same so that people have ready access to the answers, even if the questions aren't worded exactly the same. So here our examples are pairs of questions, q and q prime. The probability distribution, we can say it's two independent uniform draws from the sample of things that are on the internet forums. The labels here would be some human arbiter that says these are the same intent or these are different intent, right? So a human can do this task, and we're trying to get the machine to mimic it. This is artificial intelligence. Because the machine can do it far faster and cheaper than the humans. Humans are expensive. So those are the labels. For representing this, we can just say every vocabulary word is assigned an integer ID. Maybe it's just you alphabetize the words in the vocabulary, and you give the integers 1, 2, 3, 4 to each word. And then our questions, which are sequence of words, become sequences of integers. We now posit some family of functions that goes from question pairs to the label, these are the same or these are different. And our loss function, it doesn't need to be symmetric. Maybe grouping things together when you shouldn't or separating them when you shouldn't have different costs. So here's some table that shows the 2x2 possibilities for y and y hat. And so that's our loss function. And now our goal would be to find a function f that can compute a label on these two sequences of question words. And we want to minimize the expected loss. So that's a concrete instance of the machine learning framework. And as you think through this, some hard parts might pop out at you. Like, how do you represent examples and labels as numbers? It's not very satisfying to say alphabetize them and have a sequence of integers. What's a better way to do that? Another thing is, what family of functions can you consider? There's lots of ways of going from examples x to y, and there's lots of kinds of functions to do it. How do you select that? And then how do you minimize one? Like, how do you find the best one that minimizes this? So those are the parts that obviously stand out as hard. But actually getting the examples in the first place was what got in the way for several decades of making progress in this. It's hard to get a large number of examples, and it's hard to get them consistently labeled by humans. Human labeling takes a long time and is expensive. So these are underappreciated hard parts. But the overall framework is pretty robust, and you'll see it if you do any work in this field over and over again. It's the standard approach to these problems. So that's machine learning for natural language. So now what is deep learning? So deep learning is a subset of machine learning. We're trying to get a machine to solve some artificial intelligence task without being explicitly programmed. But deep learning says we're going to extract these patterns from data using neural networks. So neural networks is the key here. And you've probably heard about deep learning if you've been reading any of the technical press in the last 5 years. It has had a ton of hype. Deep learning is just a rebranding of neural networks, but it's been used for playing games like chess and Go. It's been used for facial recognition. It's been used for synthesizing speech. It's been used for medical breakthroughs, robotics. All kinds of problems have seen large amounts of progress coming from the application of deep learning. When you see that much press, you should ask yourself, is this real or is this just hype? And so here's a quote that I enjoy from Professor Eugene Charniak down at Brown University. He writes, "I am a long-time artificial intelligence researcher whose field of expertise, natural language processing, has been revolutionized by deep learning. Unfortunately, it took me a long time to catch on to this fact. I can rationalize this, since this is the third time neural networks have threatened a revolution, but only the first time they have delivered." And it's true. This quote, by the way, is from a book named Introduction to Deep Learning, which came out last year. I highly recommend it if you're interested in learning more. But it is true that deep learning has been around several times. And yes, you should believe the hype, but you should learn more. So let's learn more. So this section of the talk I have borrowed liberally from a course at MIT named introtodeeplearning.com. I'm going to give you a crash course in neural nets, but if you're interested in learning more, this is a free open source course that I highly recommend, introtodeeplearning.com. So let's get started. It turns out that most presentations, including this one, of neural networks are better done with images as the task, not with natural languages as the task. We'll get back to natural language understanding in about 10 minutes, but right now, let's take a quick detour into image recognition. So here, instead of doing any of those natural language tasks, we're doing a machine vision task and say, here are some images of handwritten digits. And the task is to say, what is the digit we're seeing? Is it a 7? Is it a 3? Is it a 9? What is the digit? So let's apply the machine learning framework. We need examples and labels and a way of numerically representing things. So the examples here, people write stuff, right? We just asked people to, not we, researchers at the National Institutes of Standards and Technology long ago asked people to write lots of digits, which have been scanned, and then we asked them to write 7s or 9s or 3s, and they dutifully complied. So we have the labels. All the things in the top were were created when people were asked to write 0s. All the things in the middle were created when people were asked to write 5s. And then these were scanned by machine, and you get a 28 by 28 grayscale image of this, for example, and they're pixels. And so each pixel has some numerical value about how saturated brightness it is. So the darkest pixels are 0, and the brightest pixels are 1, and the gray pixels in between are maybe a half. And so you can take this 28 by 28 image and just raster it, read off the first row, read off the second row, read off the third row, and concatenate them one after the other to make a great long vector. So instead of 28 by 28, we have this vector of size 784. And so that top image becomes the top vector. And this slightly different image of an 8 becomes a different vector. And a third rendition of an 8 becomes a third vector. And so each image becomes its own vector. So that's the examples, the labels, and the representation. And we can say that the digits are all equally likely. So our probability distribution is uniform. It's more complicated than that, but now let's think about what's the family of functions. And so here we get into the core of neural networks, is in defining that family of functions that can go from a vector of numbers to a label. And so the building block of this is a thing called the perceptron. The perceptron was first posited back in 1958, at least first published. There's some thinking that it might have been worked on as well in classified settings during and after the war. But here's the basic idea: is you take those 784 numbers, that vector of dimension 784, and you put it in at the left as input, so x1 through x784. You also put in a constant term, and you just take a weighted sum. So you just take some linear combination of them with weights w0 through wm, and there's a constant term, the 1, that goes in there as well. You sum up them all, and then you put it through what we call a nonlinearity. And I'll tell you more about this in a second. But then what comes out is some output y, some number y. So just a note: these x1 through xm, these are not multiple examples. These are multiple pixels. These are just all the pixels from one image, 784 of them. The notation was a little confusing. Sorry about that. But you just take the dot product between your weights and your input pixels, sum them up, put them through some nonlinearity. I guess I will keep the nonlinearity a secret. It's this activation function that takes any kind of inputs that might, when you weighted average them, go anywhere from negative infinity to positive infinity, and it just pushes them into this space that is between 0 and 1. And the nonlinearity becomes important in just a second. But for now, it's just a way of sort of giving us a soft sense of, did the weighted average turn out positive or negative? All the things that are very negative get mapped to 0. All the things that are very positive get mapped to 1. In between, you gradually rise, and when your sum is 0, you're at about 50-50. But most the important thing is to map it from negative infinity to positive infinity into the range 0, 1. So that's the perceptron. It's a very simple statement of weighted average linear sum. And you can see that it outputs a single label. And here it is again. It's just a weighted sum dot product. But if we want to know the thing ahead of the image we're seeing, is it a 7 or a 3 or a 9, we might need multiple outputs. So you can just do this in parallel and say that, for example, y1 will be the degree of belief we have that the image is a 1. And separately, y2 is the degree of belief we have that the image is a 2. And we could have 10 of these, 10 outputs, and then we look which one is the largest, and that would give us our belief what the image is. So we could classify the image by looking which of these is the largest, and if we want, we could look at how unsure we are. Does Z7 radically outweigh Z3, or is it close? And so there's some more notation here now that shows you have not one dot product, but 10 dot products, and not one set of weights, but 10 sets of weights. And so this is the multi-output perceptron. So here it is again, the multi-output perceptron. You piece them together, and you have a neural network, but I've done something a little bit more. Instead of going directly from the inputs to the outputs, I've added a layer. I've added a layer in between. So I'm going to do a weighted sum, but then I'm going to make not just 10 outputs, or in this case 2 outputs. I can have as many outputs as I like. And then I will take this nonlinearity so that now they're all between 0 and 1, and then I do it all over again. I take another weighted sum of these and get my final outputs, y1, y2. In this case, it would go up to y10 for the 10 different digits. And so the important reason to do this is that it turns out linear functions are rather limited. You can't do all that much with just a linear set of dot products. Dot products by themselves are fairly limited. So here's a question for us mathematically. What would happen if we did this but without the activation functions? If we didn't have this nonlinearity g that goes from negative infinity to positive infinity and maps it into 0, 1. What would happen if we didn't have the nonlinearity? Yeah, that's right. I heard somebody say it there. There's no power that you gain by doing this, because you would have W1, the weights for the first set, being a linear transform, and W2 being a linear transform. And we know that if you multiply 2 linear transforms together, what you get is itself linear, and you didn't gain anything. You might as well, if you're trying to represent some function that goes from x to y, and you choose 2 linear transforms and multiply them together, you didn't get anything that you couldn't have gotten with a single linear transform. So one of the big things that the nonlinearity g does is it lets you have a much richer set of functions than simple linear transforms. So this is the single layer neural network, 2 linear transforms and the activations after each one. So you have an input, hidden, and a final output. And so this is the multi-output perceptron. But why stop at 2? Why have an input, a hidden layer, and an output when you can have many intermediate layers? And so this is the deep in deep neural networks. If you tilted this on its side, it would feel a little deeper than if you look at it in this way. But the idea is that you cascade one after another of these hidden layers on your way from the input to the output. And each time you insert another layer in between, you have another set of weight matrices, but you get a richer and richer family of functions that allow you to model more and more possible relationships between the inputs x and the outputs y. So that's a deep neural network. And so now we have posited our family of functions f. Right? F has to be a neural network. And the parameters of it are the weight matrices. That's what we get to control. So now let's talk for a second about the loss function. Okay, so for an image recognition loss function, we're trying to categorize, is the output digit a 1 or a 2 or a 3? And so we have y hat, which you can think of as 10 different y hats, 10 different labels. Is it the 7 or not? And so we want to have something which is a high loss. If we assert that the label is true, it's a 7, when in fact it's not a 7. And likewise, a high loss if we assert that it's not a 7, when in fact it is a 7. And so this loss function breaks down into 2 parts. Is the true label 1 or is the true label 0? And this sum between I equals 1 to b is for the 10 digits. B is 10 in this case. And so you can see the charts here that if you predict 1 when the answer is 0, it's a very high cost. And if you predict 0 when the answer is 1, it's a very high cost. And in between, the cost approaches 0 as you approach being correct, because your predictions are a continuous value between 0 and 1, but the actual label is either 0 or 1. And so this is called cross-entropy loss. And so that's the common one used in classification problems. So now we have a loss function that tells us tells us how far from correct our predictions are and how we should consider being off. And so we have everything we need now to try to find a good function. We want to find a good neural network, in this case a good set of weights that minimizes our expected loss. So let's talk about expectation for a second. So we can collect a bunch of labeled examples. These are our training data. And we can certainly find a function that minimizes the loss on the training examples. Well, that's a little glib, but we can go looking for that. We can look for functions that drive the loss to 0 as close as possible. But then if we collect some more labeled examples and call these our test data, when we assess our actual classification function and measure its loss, probably the loss on the test data is different from what it was on the training data. In fact, if we have memorized the training data completely, it'll probably be quite a bit larger, and we call that overfitting. And so our goal is not really to minimize the loss on the training data. It's to minimize the expected loss over the distribution of all examples, in particular the test data are new examples. And so we need to avoid overfitting, but that turns out to be very hard to know. So mostly what we do is try to optimize on the training data, but put in various constraints or checks to prevent us from overfitting and from memorizing. Once you've done those, once you have gotten your training data, estimated the best parameters you can, confirmed on your test data that you have an overfit, you then deploy the system, and it is confronted with ongoing real-world examples where the performance, again, is driven by the expected value over the distribution. But since we only have our training data, that's what we can try to minimize, the loss on the training data. So we call this empirical loss, and the empirical loss is over the entire training data set. So you've got the sum from 1 to n, where you have n training examples. You have a loss between what you predicted, your computation on the ith training example. It's connected to the weights you actually chose, right? So this is a family of functions, f parameterized by the set of weight matrices, w. And then you compare your prediction on the ith training example with the label on the ith training example. You compute the loss function. The further you are away from being correct, the more it hurts. You add these up and you average them. And so this j of w is called the loss, the empirical loss, or the objective function. And we are trying to get it as small as possible, trying to minimize it. So the only thing we can control is the set of weight matrices. So we have the matrix at the 0th layer and at the first layer and at the second layer and so forth. That's what we get to control to try to minimize this total training loss. Yes, there's a question? Good. So the question is, do we also get to control things like how many layers we have and how many, what's the size of each internal layer? Do we have 5 hidden nodes in the layer, or do we have 500 hidden nodes in the layer? That's true, yes. So we do get to control those, and we have to choose those as well. And usually that's not done as part of this minimization. Usually there's a separate process that we call hyperparameter tuning, where we say, what if we had 6 layers? What if we had 9 layers? What if the layers were size 100 or 300? So there's some different techniques that are used for tuning hyperparameters, but yes, that's true. We also have that knob to control. So within a set of the architecture of how many layers and how wide each one is, we're trying to find the values of the weight matrices that minimize this. So this is a classic loss optimization problem. Here I've just shown it in 2 dimensions where you have W0 and W1. These might be 2 numbers in the large function, the large set of matrices. And for each one, the overall cost, the overall loss is a function of those values. And so how do you optimize a loss function like this on a surface? Well, you start somewhere. You just randomly pick a W0 and a W1. And then you compute the gradient. And you say, all right, that's how I make my loss bigger. I don't want to do that. So I'll go in the opposite direction. And I'll take a small step in the opposite direction of the gradient. And then I'll repeat. I'll recompute the gradient. I'll take a small step in the next direction, and I'll just keep going. And so I repeat this until I get convergence, and I hope that's the minimum. And so computing the gradient is the important thing, right? If we can compute the gradient, then we can do this gradient descent and just flow downhill. And so figuring out how to compute the gradient in this setup was the key advance of backpropagation. So this was developed in 1986 during the second wave of deep neural network technology and sort of revolution promising. And so they figured out how to do backpropagation as an exercise in calculus. So the goal is you have, for example, in this perceptron, you have weight matrices that connect x with y hat and goes through z1 perhaps, and so there's some chain that the connection between x and jw is mediated by these, x and y is mediated by these w's. And so if you want to make the loss function smaller, you can see what happens if you perturb the weights. And so this is an application of the chain rule, right? If you want to know what happens if you perturb weight w1, what happens to the large function? Well, it's this set of stepwise changes, derivatives. And so this is a quote-unquote simple application of the chain rule. And so as long as all your intermediate things are differentiable, you can do this. And linear functions are differentiable, so that's good. And that nonlinearity I showed you that maps every number from negative infinity up to positive infinity into the interval 0, 1, that was carefully crafted to be differentiable. And so the chain rule can be applied here, and this all works. I knew calculus was good for something. So that's it. Well, not exactly, because the surface that I showed you was rather idealized. In practice, when you have all of these, all of the data and all of the layers strung together, the landscape that you're trying to optimize over is quite messy. And it's easy to get trapped in a local minimum, and it's difficult to compute these gradients in a way out. And so when you're in practice trying to do this, there's any number of technical details. And so starting in 1952, people invented things like stochastic gradient descent, where you didn't use all of the training data all at once, figuring out algorithms for the rate at which you took steps and the learning rates, and taking large steps at the beginning and smaller steps at the end, avoiding this overfitting problem that I talked about of you do grade on your training data but not on your test data, and on and on. So these last few things like batch normalization and layer normalization, these were invented only 3 or 4 years ago. So there's lots of technical details that have been ongoing to do the optimization better, but in fundamentals, you still have this basic structure. You have a perceptron that does linear combinations of your inputs and puts it through a nonlinear activation function. You cascade these one after another, stacking them to make a neural network. You have the chain rule that lets you do backpropagation to see where the gradient is and how, what to compute the gradient. And then you use these various training techniques to do this idealized flowing downhill to find the lowest loss over your training. And that is to say, find the parameters that lead to the lowest loss. So that's the core foundation. And congratulations, you have just completed Neural Nets 101 and also gotten to 1986, right? All of this was known and feasible in 1986, but it didn't work back then. I mean, you got some papers, it showed some early promise, but it didn't really deliver practical applications. And so one question is, why now? Why has this come to fruition now if the ideas date back decades? And so to me, it's, the folks at MIT highlight that it's big data, hardware, and software, but to me, it's training data. To me, it's got to do with the data sets. And so here is the sort of chicken and egg problem, is that in the real world, if you're trying to model a relationship between an object and its label, you need a fairly nuanced model F. And by nuanced, I mean it has a lot of free parameters. So you need to find a family of functions that you're choosing your optimum among that has lots of parameters. But if you have lots of parameters, it's super easy to overfit, and you can memorize training data. Typically, if you're trying to avoid memorization, you need 10 data points for every free parameter in your model. Well, if you have lots of free parameters, you're going to need lots of training data, and gathering lots and lots of training data is expensive. And so you can do it for maybe 1 task or 3 tasks, but having to start off by gathering tons of training data is very expensive, and it's hard to do. And so what has really powered the neural network revolution in my mind is that we finally live in a world where data is more available and easier to store and easier to handle and easier to compute with. And that's really what's gotten us off the ground, is yes, the hardware and software, but to me it's largely the data. And part of that data comes from the fact that we've moved online. Our lives are now on the internet. Everybody is doing lots of activity, generating text, writing things to each other, writing and publishing web pages, taking photos and posting them, and that has become the source of our data. So as an example, folks put together a database named ImageNet, and so the ImageNet challenge was they gathered millions and millions of images. They labeled it by looking at starting with the captions or the text around the image that people posted on their web pages and such, and they reviewed it and refined it and polished it, but that was sort of the introduction. And you got this database of images, and so they put together a challenge to classify what's in the image. So they defined 1,000 categories and a task of, you get up to 5 guesses of what's in the image. And here's an example of the 14 million images. 1,400 of them are bananas. And so banana is one of 21,000 categories. And here, for example, are several examples of bananas. And the task is to guess, is this image I'm seeing a banana or something else? And back in 2012, shortly after this database was introduced, AlexNet came in, and it was using a convolutional neural network, which is a variety. It had 61 million parameters, and it could guess the correct category if you gave it 5 guesses, but it would be wrong 28% of the time. And over the last 5 or 6 years, it's gotten it down to 3.5% error rate by using vast numbers of layers and parameters in compute. But just as an example, humans, these are difficult images to classify, some of them. Humans can only do it 5% of the time. Humans make an error 5% of the time. The human error rate on this task is 5%, whereas the machines have gotten it down to 3.5%. So it really works. It's amazing that this combination of data coupled with these technologies has allowed us to build machines that can do artificial intelligence tasks. So that's images. It really works. That was our detour. Let's go back to natural language understanding. So for natural language understanding, we have some problems that are not present in the images case. So words are not pixels, and sentences are not images. So images, they are composed of pixels, and pixel values have a natural ordering. I showed it before, is between 0 and 1. That's usually given as 256 different levels of continuous variation, so 0 through 255. And the different pixel representations have a natural ordering. Lower is darker. So that comes naturally, and a small change to a single pixel rarely changes the meaning of the image. Right? You could take one of those banana pictures and change one pixel to anything you like, and it will still be a banana. Most of those things are not true for language. So sentences are composed of words, but words do not have a natural numeric value. You could alphabetize them and give them, AA aardvark is 0 and zzzix is 10,000, but there's nothing that relates the thing at position 17 to the thing at position 18. So there's no natural numeric value. The words are not totally ordered. In what order do you put trout or jumping or blouse or reciprocal? And then finally, if you change one word in a text or in a sentence, it usually changes the meaning. It can destroy the meaning. So for example, if we take the sentence, let P be any odd prime, well, let Q be any odd prime is different. If it's an even prime or P is an odd primate, these are all different. Likewise, if the sentence, they call me David Miller, you change that to they call me David Spiller, it's an entirely different meaning. And yet, it is not the case that all words are radically different from each other. Words like book and chapter and novel and essay and volume, there's something about them that's all similar. You might see them in similar contexts, use them in similar sentences. And so we need to capture this in some way. Any machine learning task requires that you represent the input numerically. And so one of the early ideas is to represent each word in a vocabulary as a vector. And so if you're going to represent it just as a number, well, instead of saying this is word number 17, you can make an elementary vector that in its 17th position has a 1, and everywhere else has a 0. So if you have a vocabulary, let's say English, and you use a 30,000 word vocabulary, maybe plus one more token to say this is a word not in my vocabulary. Then you have a 30,000 dimensional space of real values, and the ith dimension is reserved for word I. And so mango might have this elementary vector, whereas banana might have this other elementary vector. And so this is fine, but it has that problem we mentioned that you don't see looking at this, that banana and mango have anything in common. They don't have any letters in common, but there's nothing in here that shows that the words have a similar meaning. So people looked at that and said that's a problem. They also said it's problematic to be dealing with 30,000 dimensional space, and if you want a bigger vocabulary, you need 100,000 dimensional space. That's unwieldy. So people next came up with the idea of a dense vector, where for the word shall or unto or thou, we have a point in space where every dimension of the vector can have a non-zero value. And so now this is taking the geometry, and instead of saying everything's at right angles to each other, now the words can be wherever they want in the space. And so we can use dense word vectors. They can have much lower dimension. Here I'm showing examples of 100 dimensions. And now you can move the words around so that so that similar words are close to each other. So that's the idea. Embed your words so that similar words are close to each other. And this is not a new idea, right? This dates back at least to 1986, when people were trying to make distributed language models using this idea. But it was really relaunched in 2013. So there's a fellow, Tom Mikoloff, who was working at this, and he came up with this idea called word2vec. And at that point, he had 10 to 100 million words of training data from News Corpora, published news articles. And he had this idea that said, let me try to predict a word from the surrounding context using these word vector embeddings. And the idea of how to use it was fairly straightforward. You look here on the bottom right. He said, let me make a very straightforward neural network, very simple neural network, where I take a matrix W that goes from the elementary vector representation, where there's just zeros and ones, and there's a 1 in the ith position for word I, and transforms that using the matrix W to dense vectors. And then I'll have some very simple hidden layer, and then a decoding matrix, which is exactly the W transpose matrix. And my goal is to reconstruct from the surrounding words, in this case, to think of simple things, reconstruct what is the missing word. And so here we've introduced some more parameters to the function. They are the weight matrix W. Well, this is unfortunate that I've used W again, but it's the word vector embedding matrix, which is got maybe 100 dimensions by 30,000. So it's a 100 by 30,000 dimensional matrix, W in this case, and then it's transpose that maps to and from words to this dense vectors. And the parameters of those matrices can be trained, the same as the parameters in between. So you're discovering the good weight matrix at the same time as you discover the parameters of the neural network that let you predict what word goes in there. And here on the chart, what I've shown is that the predictions are, if it's to think blank of simple things, maybe it's to think felt of simple things, to think deeply of simple things, to think strongly of simple things. These are the outputs at the final node, whereas you would like, if you know that the true word that was masked is deeply, you'd like the output labels to be 0, 1, 0, 0, 0, because deeply is the only correct answer, and you train your parameters of your system to move the output towards that. So those are word vector embeddings, and here is an example of what you get. So if you run that training and you run that neural network, you get all the words showing up in space. Typically they're 100 or 200 dimensional space. Here I've projected it down to just 3 dimensions, and I've looked at what's in the vicinity of the word Boston. We're here in Boston, what's nearby, and you can see that the words which end up close to Boston are words like other cities, Brooklyn, Seattle, Baltimore, but then also things associated with Boston, like there's the Boston Globe, and there's baseball is big in Boston. And so you can see that words in the vicinity of Boston might appear in similar contexts to Boston. Here's another example for the word prime. And you can see that not only are the words around prime related to prime, but they actually cluster together about the different senses of the word prime. So here at Promise, we might think prime has to do with number theory and numbers. And you can see that there is a small cluster towards the center there that says mathematician and cardinal and odd prime and theorem. So there are words that have to do with the mathematical sense of prime, but most of these words that we see written in the training data have to do with prime ministers. And so you can see in the top left that there's the British prime ministers, and it has words like Commons and Tony, which is Tony Blair, and Margaret Thatcher is there. And then in the bottom, we have things like how prime ministers arrive. We have words like chosen and appointed and succeeded. And we have other words about how they depart. For example, in the bottom right cluster, prime ministers apparently resign or are overthrown or assassinated, or there's a coup. So not only do we have similar words to prime, right near prime, but they cluster together to things that are similar to each other. So this is good. This seems like it's going somewhere. But can we quantify that? Is there some way we can say that this word vector embedding is better than some other? We've put similar words close to each other locally. We want the similarity. But is there a global arrangement that we can strive for? And how do we assess if our global arrangement is good or not? And so what the Word2Vec system did is it said, as a proof of concept, a word vector embedding is good if its geometry allows us to do word analogies just through vector arithmetic. So let's look at what I mean by word analogies. If I have the analogy big is to biggest, as small is to smallest, that's right. So the relationship between big and biggest is the same as between small and smallest. That's a sort of syntactic relationship. A more semantic one, Athens is to Greece as Oslo is to, not Finland, Norway. That's right, Norway. So this is about countries and their capitals. And so the question is, has the system of learning word vector embeddings by trying to predict the missing word in context of sentences, has that learned enough that we can solve these analogies through simple arithmetic? So the simplest arithmetic that you can do is say, well, I've got a vector for biggest and a vector for big. Let me look at their difference and then apply that to the vector for small. So biggest minus big plus small yields what? Well, it's going to yield some vector in space. And I look around, and what's the nearest word? What's the vector corresponding to the nearest word to that result? And does anybody have a guess what it is? Biggest minus big plus small? Yeah, it is not smallest. It's unfortunate. It is not smallest. In fact, biggest minus big plus small, the thing that's closest to it is biggest. Because high-dimensional vector spaces work that way. You didn't actually move that far away from biggest. But fortunately, if you say, well, what's the second closest thing? It is smallest. And again, Greece minus Athens plus Oslo, the second closest thing, is Norway. And so it's remarkable that if you look at, for example, the vector difference between a country and its capital, those are all roughly a constant direction. And that means you can do this arithmetic and go from one country capital relationship to another. And this is true not just of countries and their capitals, but of a wide variety of relationships, semantic ones, but also syntactic ones. So currencies, cities and states. You can go from past tense to present tense. All of these relationships, the basic, simplest possible arithmetic worked fairly well. And so with a 30,000 word vocabulary, if you were just picking randomly a word to fill in the vocabulary, you'd be vanishingly unlikely to get it right. But for a database of 20,000 analogies, the system, which was learned without reference to these, was able to get the right answer almost 60% of the time, 55 to 65% of the time. And so this is remarkable. This is remarkable that one simple arithmetic operation where you compute the offset between a known pair and then you try to apply it to the to find the missing member of the unknown, works so well. And here you can see an example of several kinds of relationships that the system was successfully able to predict. So this is a proof of concept, right? It's a proof of concept that this vector space geometry is good for calculating meaning. And the geometry was come up with, the mapping of words into space was created solely by trying to predict missing words from text. So you take your text, you just blot out some words, 1 word per sentence, and then you ask the machine to reconstruct it based on the surrounding words and find the vector embeddings that make that most possible. Okay, so that was 2012, 14, I'm forgetting, 2014. Or TVEC, 2014. And so the insight is that context matters. That you can learn a good word vector embedding for a word by looking at the context in which it appears. Look at the other words nearby. That context will help you learn. But there's an observation that this system ends up giving 1 vector per word, 1 single embedding vector per word. But we know that's not how language works. In language, 1 word can have many meanings. For example, the word play could be a verb or a noun, and it could refer to sports or theater or music or the way light travels on a surface on a pond, and all of these are different meanings. So the notion of trying to capture all of this with 1 single vector in space seemed impoverished. And so this insight, the proof of concept at Word2Vec in 2014, spawned a huge ferment of research. And there were lots of different ways of trying to capture longer distance content with long short-term memory cells, LSTMs, using that for translation, trying to come up with ways of understanding which context matters at the moment. Not all the words surrounding you are important. Maybe words long ago, earlier in the sentence, are important. Dealing with how future context or right word context interacts with left word context. There was a whole ferment of research in the 4 years from 2014 to 2018, which I'm not going to have time to go through, but it has most recently led to the invention of transformers and then the invention of BERT. So I'm going to tell you a little bit about those two. Talktotransformers.com was the demonstration that wrote all of those interesting texts at the beginning of the talk, and you can go try it out now. That's using a transformer. But I want to fast forward all the way to BERT. So BERT was a system that was open sourced by Google, developed by Google and open sourced in 2018. It got a lot of mainstream attention. It was successfully applied to any number of language processing tasks and really caught the attention of the press, and has been open sourced and widely downloaded, and people are using it quite a bit. BERT stands for Bidirectional Encoder Representations from Transformers. A lot of technical words there, but here's the basic idea. We want to get beyond having 1 vector per word, because words have different meanings and different senses depending on their context. And so we want to learn to transform a sequence of vectors that represent a sentence, a sequence of context-independent word vectors, into a sequence of context-dependent word vectors. Did I say that right? Go from independent word vectors to context-dependent word vectors. And we want to do this in a way that the context-dependent vectors are good for predicting missing neighbors. So in the same way that we masked a word to do Word2Vec, we're going to mask a word here, but now we're going to try to predict it based on the context-dependent word vectors. And so here's what the setup looks like. At the bottom, we have our sequence of words, W1, W2, up to 128 words if you have them. And we will take those and mask a few of them. We know what the actual sentence was to begin with, so we know what's underneath the mask. But for now, we're going to mask them. And then we're going to put those through a word vector embedding matrix. And this is the constant context-independent matrix at the bottom, where there's only 1 vector for every word in our vocabulary. And those vectors are x1, x2, x3, all the way up to x127. And that's the inputs to our neural network. And so the thing in the middle is called a transformer. It was invented along the way here. It's a gigantic neural network. Neural networks stacked on top of neural networks, paying attention to each other and to their neighbors. It's a large transformer, has a lot of parameters. And then at the top, what is coming out is again a sequence of 128 objects, but these are no longer, and these are vectors, and they represent the words. So 128 inputs, 128 outputs, but now these vectors are not constant per word. If you have two instances of the same word coming in at the bottom, you'll have different vectors coming out at the t level because the t's know about their context. So now you have 128 context-dependent vectors, t1 through t127, and then you map them back. So the same embedding matrix, which is here shown as u, you use to decode the vector and say this vector t5 we think is word 7 or word 29 or word 100 from our vocabulary. And so we get for each of these, the yi are probability distributions. We have a guess, our guess predicted label, and that's what comes out. And for the ones that we masked, in this case y3 and y7, we compare these to what the underlying word was. So the true identity of the masked token is now revealed, and we compute, did we get it right or not? And from that, there's a loss. If we got it correct, there's zero loss. The more wishy-washy we were, the more the loss accrues. And if we completely are confident of the wrong thing, the loss is sky high. And so this is the setup. And what are the parameters here? The parameters are the context-independent vectors in the word vector embedding matrix. The parameters are all the neural network weightings within that middle blue layer. And a little bit at this top, the softmax, there's a bias and offset. So those are the parameters. Good. So once we have that, we train it all up, we get a system that is very good at predicting missing words. We can now use these representations to train a simple neural network to do other natural language understanding tasks. So here's a list of some of the ones we looked at before: linguistic acceptability, question equivalence, question answering. And how do we do that? Well, you might have noticed that there were a couple of nodes here I didn't mention. So in all of this masking and predicting what's the missing word, we have over on the left one more input token that's called CLS, that stands for classification, and one more output token named C, and there's no loss associated with it. There's nothing that drives the C towards a good outcome. It could be anywhere in this entire space, and it wouldn't affect how we nudge the parameters as we iteratively do the stochastic descent. And so this is a token used for our eventual application. So once we have trained the rest of the network to do fill-in-the-blank missing word prediction, we freeze those parameters. We freeze the vector embedding, we freeze the weights of the neural net, and we now introduce a new set of labeled examples for our actual task. Maybe it's two questions that we want to say are they the same. Maybe it's a part of speech tagger. Maybe it's a sentiment analysis to say is a review positive or negative. Whatever it is, we put the data in for that at the bottom. I think my freeze these parameters box goes a little too far. So that bottom layer can be whatever new examples we have. But this time, all of the embedding matrix and all of the internal neural net parameters are frozen. And what comes out is this C, and we have a linear feed-forward network. And so this leftmost column of the neural network that generates C is allowed to vary. And the parameters of the small linear feed-forward network at the end are allowed to vary. And that will generate some score for our task. And we compare it with the label for our task, and we have some loss. And so this process is called fine-tuning, because the vast majority of the free parameters in this neural network do not change. They were all done during the language model pre-training. It's only the things connected to the classification node and this final small linear feed-forward network that are allowed to change. So this is an example of a thing called transfer learning. Transfer learning. We're going to try to transfer what we learned about language with the fill-in-the-blank task to our particular task. And the motivation here is that learning a language is hard. For example, that BERT neural network, considered as a function, there are weight matrices and more weight matrices and more weight matrices and embedding matrices, and it all totals up to 340 million free parameters. So that's a vast, enormous space, and to train it, we need a vast amount of data. In this case, BERT is trained on 3.5 billion words, a little less, 3.3 billion words. But the magic is we didn't need to get extra human labels for these, because if you just go and collect text, the text is its own labels, right? We can take a sentence, mask a word, and the identity of the missing word that we just masked out is the label we're trying to predict. And so there's no need for additional human labeling. The words are the labels, and you can collect the data as easily as you can collect text, which on the internet is now very, very easy. Also books, text, library text, a lot of digitized text that BERT was trained on, very easy to collect. And so the conjecture is that if you learn the language first in great detail and with great nuance and awareness of context, then it's much easier to learn the task. And so when you are fine-tuning the network, the number of free parameters that's left is very small. There's maybe 1,000 or up to 10,000 free parameters. And with that, you need only 10,000 to 100,000 task-specific labeled examples to get good results. So this is the conjecture. And in today's modern era, collecting 10,000 or 100,000 labeled examples is quite feasible. We have the resources and the distributed working systems to make that happen. We can get humans to work to do that scale. It would be impossible to get 3.5 billion labeled examples. So this is the magic, right? Is that we've overcome the problem of getting labeled training examples for each new problem. We don't have to get a lot of them. And so that's the conjecture, and you can try this out by applying BERT to each and every one of these natural language understanding tasks. You do pre-training, you freeze most of the parameters, then you do fine-tuning for the task. And so the conjecture is that this will work, and so the question is, how well does it work in practice? So measuring the performance of these systems has been a problem that's been around as long as the field has been around. We've got pretty good understanding of these mechanics. We use benchmark sets. And so GLUE is a recent benchmark set. They make new ones every 5 or 10 years. GLUE stands for General Language Understanding Evaluation. It's a collection of training data and test data and a loss function or a metric to say how well did you do. And so the GLUE benchmark comprises 9 tasks that use either one sentence or a pair of sentences, and they're anywhere from is this a valid sentence to is the text generally positive or negative, does one sentence contain the same meaning as another, paraphrased, and so forth. So GLUE maintains a secret data set, the test data that they don't show anybody, but if you have a system that you think is working well, you can submit it to the GLUE folks, and they will run your system over the secret test data, score it, and publish the outcome, publish the scores, how well you did. And they maintain a public leaderboard. You can go to the internet and find the best performers on GLUE right now. And here you can see the scores are all on a scale of 0 to 100. And in addition to the 9 composite scores, constituent scores, there's a roll-up score, the average that's composited in some way. And you can see these are in the 80s, from 82 up to 90. And you can see the participants here. So this is the GLUE benchmark. And if we go back to 2014, the Word2Vec system applied to the GLUE benchmark gets a composite score of 59. On a scale of 0 to 100, it was 59. And this is a chart showing all kinds of modifications to systems and how they behave. But the key thing is that we were at 59 back then. But when you use BERT pre-trained on a vast corpus and then fine-tuned separately to these different tasks, you get from 59 up to 82. Right? And so it's hard to know exactly what that translates to. You can go to the GLUE dashboard and look at some of the examples. But this is a huge leap forward. And until then, systems were moving forward at a point or half a point at a time. And so to go from 59 to 82 is a huge jump in the state of the art. So that was last year. And last year was, so last year. Now we're in 2019. And XLNet is the next latest, greatest hotness. Something new has come along. It is based on the BERT foundation, but then uses a slightly different way of architecting things. And instead of one language model prediction, it uses a permutation over all of them. I'm not going to go into the technical details here. The point here is to say that this field is extremely active, and the improvements are coming fast and furious, and the improvement of XLNet over BERT is large. You can see that we were at 82, and variations are here now at 86 and 89. We're up to 90 on some test sets. And so if you go back and you look at the leaderboard, you can see that XLNet is now up at 88.4, and it came out 4 weeks ago, maybe. So I had to scurry and forget everything I'd learned about BERT and learn everything about XLNet, only to discover all of last week that Facebook has announced its new thing, which is based on BERT, named Roberta, and edges out XLNet by 0.1. So the revolution keeps churning. BERT is not the end of the story, I'm happy to say, and stay tuned for more developments. So there's the scores on BERT and XLBERT. So let's conclude. Good. So what are the conclusions here? Right. So the conclusions here is, I hope I've shown you that ideas are exciting, and it's an exciting time to be in my field. It's not every field that can say, you didn't read the literature for a month. Oh, I'm so sorry, you're out of date. And this is an amazing time, and it's been going for 5 years, and I have every hope that it will continue for a while. Prove or disprove and salvage if possible is what we say here at Promise. And so many of the ideas that are being put to work in the latest successes are old ideas. They're old ideas that are worth visiting again, and people have salvaged the nugget of the idea and applied it in these new ways or with these new foundations, and found that it's now the time. Now these ideas blossom and deliver on their promise. Think deeply of simple things. In Promise, our simple things are numbers and the integers and basic operations like arithmetic. Here in my field, the simple things are words. If you want to do natural language understanding, study the words. And we've gone from one elementary vector per word to a vector space embedding for words, but just one vector per word, to context-dependent vectors that can be computed on the fly from their neighbors and gather their own meaning and know which shade of the word it is. So by thinking deeply of these simple things, we can then take that model which has learned language and solve arbitrary tasks. Anyway, solve many, many tasks. And then finally, I hope I've shown you that the research in this area is a community effort, and that the ideas from one feed into the other, and it is not the isolated work of one person, which is a wonderful way to live and not be off on your own doing the research, but doing it in a community of people who are like-minded and working with each other. So ideas are exciting, salvage if possible, think deeply of simple things, and creative research is a community activity. I hope you find ways to use these teachings in your life as well. And once again, a huge thank you to Promise, to Glenn, to Margie, to David. You made all the difference in so many of our lives. Thank you so much.